Good evening, everyone. My name is Kushagra, and I'll be talking about quantum superposition and quantum coins. So, in general, superposition is the property of a quantum system being a combination of all of its possible states. A more formal definition is media. So, this property is exploited to construct a simple game which shows the fluid and non-binary nature of our computers. Talking about quantum coins is a name suggests it's a coin game to show some of the fundamental properties of a computer, which is superposition and certainty as well. The most basic unit of information in a classical computer is a bit, which has discrete values, which is 0, 1. Quantum computer uses a qubit or a quantum bit, which has a more fluid nature than a bit. Qubit can simultaneously be in a state of 0 and 1, which is called the superposition of a qubit. The measurement of this qubit reached the collapse of the quantum states to either 0 or 1, which is the wave function collapse as usual. So a superposition is created using the Hadamard gate, and as we know that a classical computer cannot create a uniform superposition, this game is unique to quantum computers. However, it has a classical version in which both the player and the computer share a 50% chance of winning. Over a quantum computer, the computer wins 100% of the time. So let's talk about the functioning of the game. So first of all, we create a circuit. In that circuit, we create a uniform superposition using the Hadamard gate. And this game can be played using only one qubit. So the ground state is the 0 state, and when the Hadamard gate is applied, the H gate is applied, the result is the plus state. So the user can choose, then obviously it's first the computer plays. The functioning of the game goes like first initially the coin is placed in heads position, then it's the computer's turn. It can choose to flip or not to flip the coin. Then the user has the same two choices, and the computer plays again at last. So there are a total of 3 moves, and in those 3 moves, each player has 2 choices. Computer makes 2 moves, and the human user makes 1 move. Since we are limited by our classical thinking, the human player can only apply next gate on the circuit, whereas the quantum computer, since it has a non-binary nature, uses an H gate and a superposition. So when two H gates are applied simultaneously, we like H gate and H gate, we get the 0 state back, which is the ground state of or the original state of the qubit. So the 0 state in this game represents heads, whereas the 1 state represents tails. So whenever the wave function collapses and we make a measurement, if the final state of the coin is 0, the computer will win, and if the final state of the qubit is 1, the player will win. So since it is the property of the circuit to recover the 0 state 100% of the times, the computer will always win. Here are a circuit diagrams. So when the user chooses to flip, we just apply an X gate for the user's turn. This first over here is this is the computer's turn, first turn. Here we have the user's turn, the human player. Then we have the computer's second move. So this 2 will give us the 0 state, whereas this is applied on the plus state. So this has no effect on plus state. At the end, we make the measurement and we store the value of the 0th qubit of Q0 into the first class field. On the other hand, when the user chooses not to make a move or to not to flip the coin. So we apply an I gate, which is just a way to say that the user didn't make a move. And the rest of the circuit remains the same. So as you can see over here as well, the zero state of the coin is recovered. Moving ahead, so here we have a little bit of code. So we use Qiskit module, Qiskit library, and the plot histogram, matplotlib random, and the IBM of course for our backend. Here we see in the how the circuit works as a quantum circuit is created with one qubit and one classical bit. We apply an H gate on the 0th qubit, which is the only one qubit we have. So adding the H gate to the circuit, this is the computer's initial move. Then we ask the user for its input. So if it's a flip choice from the user, we apply the X gate, else we apply the identity gate. Else raise an exception of incorrect choice and the program is exited. Again, we apply the H gate, which is the computer's timing move, and then we measure the circuit. So we'll execute this circuit on the IBM QX2 backend with only one shot. Since we say that the computer will win 100% of the times, even if the shots are more than one, the computer will win 100% of the times. We get the counts and we see that its count if I in counts is 0, which is the 0th value of counts. We print that the computer has won, and if we print that the player has won. At the end, we can again plot the histogram if we want. This line has been commented out. So here's the sample output. So we just ask the user, nothing else, choose to flip or not flip. The user chooses to flip. Irrespective of what the user does, the computer wins. And why? We know that later. So here are the few important characteristics which are formulated as questions. So what happens when you apply the Hadamard gate on the coin? So the Hadamard gate on the coin changes the 0 state into a plus state and the 1 state into a minus state. Since we are applying it on a 0 state, we get a plus state and a uniform superposition of qubit 0. With the gate, so it changes the 0 state to the 1 state and the 1 state to the 0 state. Basically, it changes the heads to tails and tails to heads in a classical system. When it is applied to a plus state, it has no effect. So we see that when a Hadamard gate and an X gate is applied, the Hadamard gate on 0 changes to plus state, and the X gate on the plus state the plus state remains unaffected. So applying a Hadamard gate, an X gate, and an Hadamard gate, which is the circuit when the chooses to flip the coin, the final state of the coin is recovered, or the initial quantum state of the coin is recovered. So hence we get 0, which is the ground state. So what happens if you apply an X gate and then the Hadamard gate? So this is not related to the circuit, but it's still quite informational, since applying an X gate changes the qubit from 0 to 1 state, and applying the Hadamard gate on the 1 state changes it to a minus state, which is nothing but 0 minus 1 over 4 over under root 2. The probability of 0 is still 0.5 and minus 1 state is 0.5. Since even if the position was created on a plus state, which means that an X gate is applied before the first X gate, we'll still get 100% times that the computer will win. So executing the circuit n times. So as per the logic circuit diagram, any input by the user will give 100% output of 0. The complexity of the algorithm which is available, which is applied, is big of 1, and big O notation is 1. Because the circuit no matter what the user does, it returns the same output in the same amount of time. However, it depends on the backend. So in the real world, however, due to environment noise, the actual results can be a bit off in the ideal results, but most of the times we get the correct output. Here, the complete game is represented as a flow chart, which is that we begin with the initial zero state. The computer plays, it applies the H gate, we get a plus state. Then the user chooses to flip or not, it applies the X gate or the I gate. Irrespective of what the user does, the plus state remains intact. Then the computer applies the final H gate, which gives us the initial state, which is the zero state. So thank you. That was all from my side, and there are a few contacts information of mine. This presentation is also available. Thank you.